I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, thank you for the students. Just ask you to bless this class, Lord. In your name I pray. Amen. All right, let me start with just telling you where you can find a copy of what we're looking at today. On my website, I mean, you could just go directly from the up here, right? Go away, other stuff. So it's www.supermath.info, ANOMALIS_39_91.pdf. So this is anomalies. Actually, this is the wrong one. This is the second one. We want the first one. So 138. Let me show you where this is coming from. On my old, okay, so on my website, Matthew, angry Matt, you get no soda, get angry. Where was I? Links of interest to past and present students. On here, there's my old NCSU webpage, which you go click there, and then in the old NCSU webpage, if you go down, I've got links to some various things. This is the Richard clause, but it's from another time. And let's see here, the Richard clause. I wonder what Richard's up to. Let's see here. And then these are notes from Dr. Fulp's Anomaly course, 2005. We'll look at both. I'm going to start with the 1 through 38. So you found them? Yeah. Okay. You guys good? All right. Okay, so let me, can you see everything there? Yeah. Yeah? All right. So, again, this is a course that was taught by my advisor, Dr. Fulp, Ronald Fulp, fall 2005. And the books we were using included Bertelmann, Nakahara, at that point probably the first edition, although now there's a second edition, and also Bleeker's. The book by Bleeker, if I recall correctly, is now a Dover book. It's about 200 pages. It's packed with really good mathematics. But anyway, so this is a brief discussion of the course, not all of which we'll cover in here. So we'll start with the basic stuff just to get warmed up. So we started by talking about differential forms. You got P forms, you got L forms. Einstein summation notation going on here, right? This is a formula for a P form. Let's see here. What's this down here? Looks like an L form. Calculate the wedge product of them. That's a formula for the wedge product using the Einstein notation. Very simple, right? The details, here of the wedge product. Well, who cares? This is too much. Anyway, the point is you can define the wedge product of two differential forms. It satisfies this wonderful algebra, as we have talked about before, distributive, associative, skew, graded commutative. We can define an exterior derivative, as is done down here. You can show that that's coordinate invariant. In particular, it satisfies these rules. It's linear. It's graded Leibniz. This is an example of the Koszul sign convention. T squared is 0. It's been said that all the equations of physics are included in this identity. It's only slightly an exaggeration. You could also define the exterior derivative by these sorts of formulas. For example, the exterior derivative acting on a pair of vector fields is given by basically the evaluation of x on the function formed by contracting the form over the other vector field minus the other vector field acting on the function formed by contracting the form over the other vector field, and then minus the form acting on the Lie bracket of the vectors. So this is a formula for the exterior derivative, no coordinates, right? And that generalizes down here to a P form. This is how you could define the exterior derivative of a P form. without coordinates, just as it acts on a p plus 1 tuple of vector fields. Great. So this we'll use for vector fields. This is the alternating tensors, which, let's see here, what's this notation mean? That's a vector, yeah, vector field. I think it, I mean, this is, yeah. Well, the alpha is an element of alt that. I think that means that alpha is an alternating map which takes in vector fields and spits out smooth functions. It has the structure of a module over the ring of smooth functions. It's not a vector space, right? And I wish there was a, I need to get, this is only $6. I only have this much scrolling. I don't have like in-between scrolling, which is sad, but. Wireless mouse. Would that work immediately? Should? Let me try. I'm going to try it out. And I can just use the laser. While you're looking for that, I will continue on here. And we talked about a lot of this stuff in the advanced calculus, right? How patriotic. Let's see here. You know, I should really get one of these for my house, because we watch stuff on a computer. Now I was getting up and going over to the computer and doing stuff. I'm dumb. This is what, like $10? Yeah. Ooh, wow, nice. So, where was I? What's this here? Oh, the Lie algebra cohomology, the alternating paired with the exterior derivative. This actually defines a Lie algebra cohomology. But I guess that's for another day. Come on. You can talk about interior products. Dr. Norris's notation. The hook, X hook. And so the interior product will take a P form and convert it to a P minus 1 form by basically, contracting one of the inputs to the form. It also has nice properties that will be given down here eventually. For example, the interior product of a form with a vector gives us just the contraction of the components of the vector across the form. If you can take a 2 form and turn it into a 1 form by contracting with a vector field. Here's the properties of the inner product. Linear. You pull out a function. You got this funky it's again kind of a derivation, right? It's a graded derivation. Interior of x, wedge beta, plus minus 1 to the degree alpha, alpha wedge interior of beta. Oh, the interior product is also squares to 0. Okay, so we're setting up the basic algebra here for the course. Next, we talk about metrics on a manifold. Metric is a symmetric, non-degenerate bilinear form. So here we allow for the case that, you notice there's no assumption of positive definite, so this is not an inner product necessarily. It includes things like ones listed right here. It could be, for a 2-dimensional case, it could have this as its matrix. That's possible. So let's see here. When G is defined on M, we assume that there exists a covering of M with charts such that the matrix of G, what's this, G alpha beta? Is it 2-dimensional? It's weird. I'm not quite sure what this is saying, but I think we should go on. Then I introduced I didn't introduce, Dr. Fulp introduced the Hodge Dual in a beautiful way by basically introducing it as the musical morphism with respect to the wedge product, inner product. So the inner product of alpha and beta, where alpha and beta are both P forms. You can raise, let's see here, raise the indices. Basically what this is alpha with the index up, contract against beta with the index down. So this is an inner product of alpha and beta, both being p-forms. The G upper mu, of course, is the inverse metric. And G tilde is a mapping from p-forms cross p-forms to smooth functions. So if you fix a point, it's just a plain old garden variety inner product, I think. Remember, we assume our manifold supports Euclidean or Lorentzian metric. Measuring each neighborhood of a point, there exists, meaning that in each neighborhood of a point there exist vector fields, E alpha, such that G of E alpha beta is equal to eta AB. This eta AB is assumed to either be the identity matrix or like 1s and -1s on the diagonal. So, in other words, that there exists, in each neighborhood there exists a G-orthonormal frame. Let's see here. Anyway, moving along. Orientation on a manifold is an everywhere non-vanishing M form, something like this. So either we'd have that's positive or that's negative, and it's clear we could either make it positive or negative. So if not to begin, you simply change, flip one of your coordinates to minus the coordinate, and that will change the coefficient of mu to minus what it was starting. So without loss of generality, if you have an oriented manifold, you can assume that you've got a top form with a positive coefficient. Stop that stupid thing. I don't know how to make that stop. But, all right. And let's see here. What am I getting at? So if we have an oriented manifold, then we have this top form, the determinant of the Jacobian of the transition function is positive for all overlaps. All right, anyway, I should move along here. I don't think this has too much to do with what I want to tell you guys today. All right, so if we have a metric on a manifold, then we can define mu G, and suppose mu G is a compatible orientation, then each point x and m, there exists a unique linear isomorphism from k to m minus k forms, such that for alpha a k form, beta a k form, we have alpha wedge d, this is what we're defining implicitly, the Hodge dual of beta. It's the G tilde alpha beta, all right, times the volume form. So, in other words, this is a k form, this is an m minus k form, so we have a total of an m form, but mu G is a given m form. And so this implicitly defines star beta. Here's the formula for G tilde. So here's the, so Bertelsmann, which I think I brought here for you guys at one point, is the red and blue Cambridge book. I was carrying that here the other day, but anyway, here's the formulas in Bertelsmann. He writes, like the Hodge dual of the dx's is this, where this symbol, look at this thing. So you've got the antisymmetric symbol with indices raised is a notation for impliciting, inverse metrics and so forth. There's all kinds of sneaky notations used in physics. And then worse yet, this scales with a metric. So this symbol would be E tilde. This is the Levi-Civita symbol, and that involves a square root. I don't know. It's been a while since I've gone through these things, but they play games with this epsilon symbol. It's not just a combinatorial thing in certain contexts. It actually includes in it the square root of the determinant. The square root of the determinant of the metric, rather. So anyway. All right, so getting to the point, there is something called the Hodge dual, and it's kind of almost involutive, but not quite, because there's a sign, right, that involves the dimension of the manifold, the degree of the form. So it could be that the Hodge dual is the thing again, but it could be minus the thing. But it's either plus or minus what you started with if you take Hodge dual on a form. And it's different if it's Euclidean versus it's Minkowski. Notice the Minkowskian has a +1 here. The Euclidean does not. So it depends on the signature of the metric. So here's some explicit calculations, like the Hodge dual of 1.
Is there a generalization for that for other metrics?
What's that?
Is there a generalization for that for other metrics?
You mean this?
Yeah. We got both these.
Oh, Euclidean, Minkowskian. Yes. Formulas are known for this for, if you have a metric with signature R, S, there's a formula for the Hodge dual with respect to that, yeah. So if you have more minuses rather than just one minus or something like that. At the start of this, we defined Minkowskian as, I think, having 1 minus 1. You can either have 1 minus 1 and a bunch of pluses, or you can have a bunch of minuses and 1 plus. I mean, you kind of, the thing that makes Minkowski different than like more general Minkowski-like stuff, I think, I would say Minkowski has one time coordinate. I mean, you could think about one-dimensional Minkowski, you can think about two-dimensional Minkowski space, or three-dimensional, or four-dimensional. I think that the thing that would make it Minkowski, in my thinking, would be it has one time.
The Minkowski measures it's a negative.
It could be, it depends on the book. It depends on the book, whether it's, I mean, the two choices for the Minkowski metric, if you have Minkowski metric acting on a pair of 4 vectors, it's either minus time plus the dot product of the spatial parts, or it's the time component times the time components minus the dot product of the spatial parts. So you can either go either way. But anyway. Fortunately, Sylvester's theorem says that there exists a basis in which, at least at each point, you can take the symmetric non-degenerate bilinear product and put it in the form with 1s and then minus 1s down the diagonal. Sylvester's theorem. Anyway, I digress. So here's some Hodge duals. We don't really care that much. I don't think. The Hodge dual of a 2 form is a 2 form, and this is kind of like, I always think about those snakes that you hold in your hand and go like, and like it's got a little bit of room, and then when you squeeze it, then like it goes to the other spot, and if you squeeze that, it goes to the other spot. You know what I'm talking about? Like these little, like stress relieving snakes with balloons in them or something. I don't know what it is, but so like 2, 3 goes to 0, 1, and up here 2 goes to 0, 1, 3, and there's a plus or a minus depending on the details, and so on. All right, so here's where we're going. What we want to be talking about at this point is the connection on a principal bundle, which is omega, the curvature of the connection, which is omega, little omega, big omega, like omega. Omega! I'm not sure. How should I distinguish these? But they're both omega, right? Capital. What? Low mega and bomega.
It's a suggestion.
All right, I'm going to go on. So I did ask for a suggestion. That was my mistake. Let's see here. Connection. A connection. We use A for the connection, F for the field strength. The dual, the Hodge dual of F, is also a 2 form. The Yang-Mills Lagrangian can be written something like the integral of F wedge the dual of F. The formula for F looks like that. In the electromagnetic case, it's on space-time, 4-dimensional, and you've got electric field components here, magnetic field components there. So this one 2 form contains both electric and magnetic fields. And beautifully, the Hodge dual actually corresponds to something called complexion, which is some sort of EB interchange. It's not quite that, but it's something like E changes to B and B changes to E, but there's a factor of C involved if you study it more carefully. It's pretty neat. That is discussed in Misner, Thorne, and Wheeler's gravitation. That complexion thing I was talking about, there's a text box on it I can show you if you want. Anyway, so Maxwell's equations, of course, dF equal to 0, or d of the Hodge dual of F equal to J, which is the Hodge dual of the current 1 form. All right. Next day. Oh, we're still in August. We got to get on with it. Page 12. And what's my time? I'm going to have to pick up the pace. I'm going to have to pick up the pace because we're on a timer. So you can define an inner product on p-forms by integration over the manifold like this. So you take the integral over the manifold of the wedge product of alpha with the Hodge dual of beta. For this integration to make sense, either these forms have to be only non-zero. I mean, there has to be some assumption that the forms are not non-zero too much if m is big, right? I mean, there's got to be some notion of convergence here, right? What's that? Yeah, compactly supported, something like that, exactly. But I think we'll focus on the algebraic structure here mostly. Anyway, so alpha and beta p-forms, assuming alpha and beta are suitably chosen such that the integral is sensible. Note that star beta is an m minus p form, so this is in fact an m form, and it makes sense. We can integrate an m form over an m-dimensional manifold. That's how integration works, right? If you want to integrate a three-dimensional form, you better find a three-dimensional space. If you got a two form, you better find a surface. If you got a one form, you better be integrating along a curve, right? None of this nonsense we learned in Calculus 3 about vector fields being integrated over both curves and surfaces. What kind of nonsense is that? Let's see here, anyway. Whoa. Well, there's a calculation. So, there is the formula for this wedge product in terms of upper and lower indices of the form, the coefficient of the volume form. There it is. Great. Anyway, there's also a co-differential, which goes the other way in terms of Hodge dual, d Hodge dual, and this handy-dandy sign factor. It's a co-differential because it goes the opposite direction. It increases the form degree, right? So this is a picture of what's going on here. We start with a p form. We Hodge dual to a p minus 1 form. We exterior derivative to p minus 1 plus 1 form, right? Then we Hodge dual again to a m minus p plus 1 form, which, by the way, is why is there another arrow here? I think I should just have equal, right? This doesn't need an arrow. Why did I put an arrow here, idiot? This is just equal. What's this equal to? M's cancel, right? You get p minus 1. Or p plus 1? P plus 1, right? Wait a minute, no. P minus 1. Oh, right, the codifferential lowers the form degree. The exterior derivative does what? Increases degree, right? I take the exterior derivative of a p form, I get a p plus 1 form. So a coderivative is the opposite kind of thing. It goes the other direction. These are very interesting, the interplay. If you use the exterior derivative and the coderivative together, you can put them together and make the Laplace-Beltrami operator, which is essentially the Laplacian in the abstract. I think I had homeworks for you guys on this, yeah? Yeah. All right. Fiber bundles. Yay, finally, back to last class. So, we to say that E, M, F, pi is a fiber bundle means that E, M, and F are manifolds, the bundle space, the base space, the fiber, the standard fiber. We have a projection, pi, from E to M, which is a smooth surjection. I think I forgot to emphasize last time, it's a surjection. That's kind of important. There exists an open cover of M and a family of maps, psi alpha, from the inverse image of the open cover to the Cartesian product of U and F called local trivializing maps, such that for all alpha, the map psi alpha is a diffeomorphism and the diagram below commutes. So this is something that was fuzzy in my mind talking to you last time. I knew I was missing this concept. I admitted it to you. Here it is in gory detail. So over the inverse image of each thing in the open cover, there's this set up in the total space that is diffeomorphic to the Cartesian product of the chart across the standard fiber. This is a formalism to make precise the intuitive statement that a fiber bundle is locally a Cartesian product. This is what's meant by locally a Cartesian product. Here's a picture. So you got your total space, you got your base space. Here's one of your local trivializing charts, chart domains down here, and an inverse image up to some inverse image of the U alpha up here in the bundle, and then the psi alpha takes you from that over here to a boring plain Jane trivial bundle Cartesian product of U alpha and F like that. So as I was telling you, pi inverse of x is bijectively corresponding to f, like that, according to this map. All right. A trivial bundle is not twisted. Here's one that is twisted, the Mobius band. So the Mobius band is, you know, basically just well, we can take a piece of paper and make it. The base space is the circle, and the pi is pictured in the picture, and there it is. Let's see here. Transition functions. Will should have principal bundle for that terminology. Oh, in other words, this isn't technically transition functions yet, but they're like transition functions perhaps. But if we were to look at the composition of psi beta and psi alpha inverse like that, then that would be a mapping from what to what? From this back to itself, right? So it goes over here, and then back here, So this is a mapping from the intersection of u alpha, u beta cross f to u alpha cross beta, uf. It's that kind of map. And so if you look at that, it fixes x, right? If you actually sort through this in the definition of the trivializing map, it's going to take this x, map it over to like x comma f, but then the inverse, then the inverse map is going to take x comma f, map it over to here, to the in the fiber over x. Then the psi beta map takes that fiber over x and maps it to x comma some other f. Now, the relation of this f here and whatever is over here, well, I don't know what that is. It's complicated. It involves this piece of the transition function. But anyway, if we fix the x and we let f vary, we get a mapping from f to f. That's fairly clear, right? If you just ignore the x and just focus on this mapping to that, what you have then is a function from the fiber to the fiber. In fact, these form a group called diff f. It's a huge group. That brings us to vector bundles, in which case is a specific case of the fiber bundle where we take the standard fiber to be a vector space. There exist smooth maps. Let's see here. Sorry. What do I got here? I've got the total space, the base space, the fiber, the projection, right? But the fiber is a vector space. What's this 2? Can you guys tell me what I'm saying in 2? There's addition and multiplication. It must be addition and multiplication. That seems fair. Apparently I'm using k for a field, right? I really want that to be f cross f. But maybe I remember things wrong. Let's go on here. I mean, is it saying we have a way of adding and scalar multiplying the total space? I mean, that would seem to be saying we have a way of adding and multiplying things in the total space, right? So if I take v and w and the Cartesian product of e and e, such that pi of v is pi of w, in other words, they're vectors. I guess that makes sense. So what we're saying is you take a pair of vectors you take 2 vectors in the total space, right? That are in the same fiber. See, because pi of v is equal to pi of w, which is to say that they're over the same point in the base space. Take 2 such vectors, then you can well, on that set of things, you can define addition and scalar multiplication. All right, fine. So what it's saying anyway is that each fiber is a vector space. Okay. The local trivializing maps, right, from the inverse image to the Cartesian product of U and F are such that for each alpha and each x in U alpha, the mapping from pi inverse of x to F defined by U maps to pi F. So this pi F means projection onto the fiber component. I mean, this is a two thing, so like pi F of U comma F is just F. Is an isomorphism of vector spaces. Let's look at the picture. That might help. So let's see here. Where's U? U is in here somewhere, right? So U maps over here to pi F of psi alpha. So psi alpha of U is something over here. It's a pair. It's a pair which is like a point in the base manifold with a vector, right? And so what this map is saying is it's saying you take a point in the fiber, right? And you map it over to the pair. Ignore the point in the base manifold in the pair, and just look at the fiber piece, the vector piece. Then that's an isomorphism. Let's see here. So basically, pi inverse of x is a vector space because pi of pi inverse of x equals to x for all v and w in pi inverse of x. Whoa. Whoa. Where are the v and w here? It's blowing my mind. I'm going to go on. I don't think I'm wrong. I just don't think I'm right. Okay, so moving on. Principal fiber bundles. PFB, principal fiber bundle. You have the total space, the base space, the projection map, and a group. This time our fiber is a group. A Lie group, which acts freely on the right of P. What's that mean? That means that there exists a smooth map, sigma, from P cross G to P, such that if we look at U dot G, which is sigma UG, it has the usual action properties. So it's got this kind of associativity, relation. The identity in the group acts like not moving anything, right? And on the other hand, if when you act on an element, you get the element back again, well, that means that you're acting by the identity element. So this is what it means for the Lie group to act freely on the right of P. Okay. The orbit, U dot G, is precisely for all U and P. Let's see here, what's this saying? I mean, I think the way I understand that is that if you take a point in the total space, in the fiber over U, where is U actually? U is in the total space, let's say. So suppose X is in the base space, right? And if you look at pi inverse of X, that gives a fiber over X, right? If you pick any point in that fiber, let's say U, and you let G act on it on the right, according to this right group action, this free right group action of P, of the Lie group on the fiber in P, then it's saying it's transitive, I think. I mean, the orbit, is that what it's saying? I mean, pi inverse of pi of U. Yeah, I think that says it's the whole fiber, right? Let's say pi of u is equal to x. This is pi inverse of x is equal to u dot g, where that u dot g is, you know, it could be anything in the fiber over x dotted with g. It gets the whole thing. So it's I think you could say it's like it's a transitive action on the fiber. Yeah. There exist local trivializing maps, like so, such that for each u in the fiber over u alpha, we have that. And look, so now, so for a vector bundle, the local trivializing maps, they maintain something about the vector space structure of the fibers, right? That's what we saw. Now here, the local trivializing maps, they respect something about that group action on the fiber that we're talking about. In particular, that if we take psi alpha of u dot g, it's psi alpha of u dot g, where this on the right-hand side is an action of the group on the trivializing space, u alpha cross g, which is to be defined right here. So the pair x comma h, which would be in u alpha cross g, h is an element of the Lie group. When we take the action of g on the right with this pair, it's simply defined to do nothing to x and to multiply h by g on the right, like that. And so we have this property for the trivializing maps. There's a correspondence between the way the group acts on the fiber and the way the group acts on the trivializing space. And it corresponds naturally. So here's a picture, what we were just struggling with. So you have u, this would be u of g1, u of g2. As you sort through different group elements, you trace out the whole fiber under the right group action of the Lie group on the fibers of the total space. And there's a one-to-one correspondence between the fiber and the group. Basically, over here, fixing the point with the trivializing map. Anyway. So the group action moves up and down the fiber. UG1 equal to UG2 implies UG2 inverse equal to U, which implies that G2 inverse is equal to E, which implies that G1 is equal to G2. So you have a one-to-one mapping of the group onto the fiber. So there's a, see that? If we have these two are equal, that, annoying. If we have these two things in the fiber are equal, that implies that this is equal, which implies that that's the identity, which implies that G1 is equal to G2. So these 2 points in the fiber over pi of u are equal if and only if the group elements G1 and G2 are equal, which means that there's a one-to-one correspondence between that fiber and the group. Does that make sense? Yeah. All right, so if we have a principal fiber bundle, P, M, pi, G, and we have a chart on M, a section, I talked about this a little bit last time, local section of the principal fiber bundle is something that when we compose with the projection, we get back to identity on U. And of course, the section has to be smooth. Here's a sad picture of it. It's easy to prove that S of U is a submanifold that cuts through each fiber only once. So suppose you have a local section, then you can define a local trivializing map, psi U, as follows. See this? So if I'm given a local section, I can define a local trivializing map as follows. I take SXG, which is going to, that's going to be a specific point in the fiber over X, right? And that maps to X comma G, and you can sort through the fact that that satisfies the axioms that the local trivializing map on a principal fiber bundle must satisfy. So you could also, okay, so you can take this work. Is it fair to define it on that? Well, you can show you can show such a trivializing map exists as follows. Define this map. This is inside baseball for us. All right, so suppose, I'll move along here. Suppose you got a bunch of local sections, like 1, 2, 3, 4, theorem. If U is a subset of M, then there exists a local trivializing map, like this, if and only if there exists a local section of U to P. So these are equivalent concepts. You can interchange, you can trade back and forth between local sections and local trivializing maps. How do you do it? The last page, we sketched the proof of given a local section constructing the trivializing map. That was the formula we looked at. Here's the converse direction. If I'm given a trivializing map, how do I construct the section? Well, we define SU from U to P, which is what we want, from here up to there, by SUX. It sucks. Sorry. Psi alpha inverse of x comma e. I think that makes sense because this is in the manifold across the group. The inverse of the trivializing map takes us back to the fiber over x. And so this is definitely the right kind of formula. And then you just have to sort through the details so that it actually satisfies the needed, that it plays nicely with the group action like we want. Oh. Let's see here. Edit. Yee. Ooh, that didn't help. Really? Don't be a moron. Adobe, this is why I don't use you anymore. These are some relevant examples from, I believe, the first edition of Nakahara. Wait a minute. Well, now I'm confused. Is this Bertelmann or is this Nakahara? I feel like this is Nakahara. I might show you these guys another day. I've got a 20-page PDF I wrote myself exploring the Hopf and the direct monopoles, which has to do with kind of neat particular formulations of... talk about that later. Anyway, I'm going to try to get past this. Oh, what's this? I don't know, it's too ghostly to read, so let's move on. Oh, this is also ghostly. Oh no. I hope it doesn't stay so ghost. Let me try and view. I think I chose poorly. Well, what does they say? One right doesn't make a wrong, but three rights definitely make a left. Something like that. No, it's not quite the saying. I don't know. What on earth is this? Don't know, don't care at the moment. Let me move on here. This is some particular... those are particular formulas for a particular question, which is not particularly interesting to me at the moment. Next up here, we have a family of local trivializing maps on a principal fiber bundle. Then we can define a family of maps G beta alpha that do what? They go from the intersection of two local trivializing charts to the group. How do you define these? In particular, what? Where are these where is this U alpha and U beta, guys? Yeah, I want to say it's in the base space, but then... Oh, but this up here, so that's in the base space. X is in the base space, but this right here, it's something what? This is a base space element and a group element. So this would be in like the Cartesian product of U alpha intersect U beta and G, this pair right here, right? And he says that is defined to be psi beta composed of psi alpha inverse of x comma e. Here's a picture. So let's think about this. Over in here somewhere, we've got the identity, we've got x comma the identity element, right? Right there. We take psi alpha inverse of that. That moves us all the way over here. Chunk. And then we take psi beta of that. That moves us back over here. Chunk. We're on the same fiber in the Cartesian product of you know, U alpha intersect U beta and G, but we're maybe at a different group element. So we've moved in the group but stayed on the same fiber. That's why this defines this G beta alpha X, right? And let's see here, what do we do? Let's see, what am I doing here? So I'm taking a local trivializing map of X comma this G function we just defined, so this is equal to that. How does this work? What's going on here? How do I get from here to here? How do we get from here to here? Does that make sense? Oh, look here. If we calculate psi beta inverse of both sides, we get what? Psi beta inverse of, stop that, you stupid bar. I think it's just acting on both sides by psi beta inverse here, right? I get, stop that. I think I'm using one of the properties of the trivializing map that I can pull the G out. Because remember, G beta alpha of X is a group element, and we have those properties for the trivializing map that we can pull the group multiplication out to the right. I think I'm using that right here, right? I think that's what's happening there, going from here to here. But then, what is this? Well, this is S beta of X. That's the local section. And that's the G beta alpha X, and there's the local section. So again, we're using the construction of local section from the local trivialization. That thing again. And so there you go. Two local sections on overlapping chart domains. How are they related? At a given point over the base space, there's some group element that when we multiply on the right, the one local section will get to the other. Makes perfect sense. It makes perfect sense what we got to. I mean, it's just here's a picture of it. So maybe that's S beta of U beta. This is S alpha of U alpha. If you pick a particular fiber, the G beta alpha takes you from one to the other. I forget which one to which one, but I'm not sure if it goes up to down or down to up. I mean, anyway, okay. So, what's the point here? Gauge transformations on the space of maps. Okay, gauge transformation space of maps, which is infinite dimensional, all right? Not hard to prove that if we had a triple intersection, alpha, beta, gamma, that to go from gamma to alpha, we could also go from gamma to beta and then from beta to alpha, which you can almost visualize, right? Because you have these three sections. You go from the bottom one to the middle one, from the middle one to the top one is just the same as going from the bottom to the top, skipping over the middle. It makes a lot of sense. And this is this is not check. That is not how you spell check. It's the check cocycle condition. Check is a name. It's not like check. Sorry. But anyway, these satisfy what's known as the check cocycle condition. Oh my goodness. Why are we talking about geometric quantization now? Ay caramba. There we go. There's how you spell check. Check cohomology. Anyway, this is an interesting comment. I'm not sure. I want to move on. All right, so we're now in the next class meeting. So the point is, we have an open cover of a manifold. We've got a family of maps, G beta alpha, which are mapping from the intersection of the charts to the group. They satisfy these check conditions. And by the way, this is the theorem I was telling you about, that if I give you a base manifold and I give you these functions from intersections of the chart domain on the manifold into a Lie group that satisfy these conditions, then you can prove that there exists a principal fiber bundle that's formed from gluing these things together. So in particular, where the principal fiber bundle has a family of local sections whose transition functions are exactly these given cocycles. Remark. Physicists work on M. They tend to work with local gauges defined in some neighborhood of spacetime, which is to satisfy the above criteria. So then they can build a principal bundle or not. In other words, physicists will say that these conditions are met for the gauge functions because of physical reasons. Yes. Here's how you'd actually build the principal bundle. You take the disjoint union of the group with the charts, and then you quotient by this equivalence relation, which basically makes the proposed local sections local sections. So the kind of usual story. Work on a disjoint union, quotient by the thing you want, get what you need. All right. Anyway, not particularly interesting to our current purposes. I'm going to move along. Oh, Yeah. We don't care. All right. What about vector bundles? How to build vector bundles? Do we care about how to build vector bundles? I'm not sure we care. Apparently, to build vector bundles, if we were given matrix multiple, anyway, this is going to describe how to build vector bundles in terms of, well, anyway, anyway, you can build them through some similar thing. Let's see, where are we? So I told you guys about this one last time. The frame bundle is a principal fiber bundle. The bundle space is P comma EI, where the set of EI is the basis for the tangent space of P and M. The projection map takes the frame at P and just keeps P. You let GLM act on frames like so. So P EI is P comma EJ. There's a summation over J here. So this is just basically the invertible matrix or invertible transformation acting on the basis to give you a new basis, a new frame. And let's see here. If U is the domain of a chart, the local trivialization would be a map from in the frame bundle to Cartesian product of the base space with invertible matrices. There's a formula for it. All right. Okay. All right. 2, if L is a Lie group and H is a closed subgroup, then L over H, eta, and H is a principal fiber bundle, where eta is the usual coset map, I think, right? We go from the Lie group to the quotient, the factor group. Well, this doesn't have to be a factor group. I didn't say that H was normal. H is a closed subgroup, so this L mod H doesn't have to itself be a group. It could be just the set of, well, left cosets apparently. But that's another way to define a principal fiber bundle. What would the group be here? The group would be H itself. So you can, what's the base space? Oh, I don't know. I'm sorry, guys. Again, I'm trying to forge ahead here. We talked about the tangent bundle last time. I tried to be somewhat careful on that with you guys, just to try to build some intuition before I got crazy today. Hopefully it worked. I don't know. This probably we should look at for just a second so we understand the notation. So psi u, here's this thing in the tangent bundle. It's P comma a vector. And what is the tangent? Oh, this is really pretty. So check it out. You take something in the tangent bundle and you map it to a point, comma, same components, right? But what's this script R? Script R is the standard basis. So that's essentially the adapted coordinate chart I wrote for you guys. Well, not exactly, but it seems awful related. If you look at overlap, you end up with the transition functions, which are assumed to be smooth. All right, we talked about that. All right. Oh, now we're in reruns. Let's see here. Ooh. Hey, there's why this is equal to that. That's kind of cool. Seems like this would have been nice to find when I assigned you that as a homework problem, eh? Did I assign this as a homework problem? This feels like an advanced calculus homework problem, though, doesn't it? Should be. If it's not right now, it should be. Look at all these steps. Ooh, I love it. Prove the product rule using Stokes' theorem. That's benign. Oh my goodness. Yowzers, Bowsers. All right, so some formulas for the Laplacian and the... Man, this is fun stuff. But, oh, here's a definition. Phi is harmonic if triangle phi, what? I think equal to 0. Okay. That's a theorem in Warner says that the de Rham cohomology class over the manifold is the closed forms mod the exact forms. The exact, d alpha 0, every exact thing is closed. Recall exact phi is that. The Hodge theorem says that every de Rham cohomology class contains one and only one harmonic form. Then the harmonic forms then are essentially the de Rham cohomology for M compact and Riemannian. Anyway, note to yourself, study de Rham cohomology when you get a chance, because it's neat. Then next we talk about associated bundles. All right, what's an associated bundle? You know what? Fine. It's endless. There's so much. All right. I guess in my defense. What's that? Yeah. Well, it's halfway through. There's another PDF. You got one more day of this. So bring your coffee. All right. So continuing with my maximum compression lecture. If an associated bundle, if we have PM pi g, a principal fiber bundle, and if g acts linearly on the left of a finite dimensional vector space V over K, then we show that there exists a vector bundle E associated to the principal fiber bundle and this action. So an associated bundle is a vector bundle which is associated to a given principal fiber bundle in a natural way. That there's some kind of interface between the vector bundle and the principal fiber bundle. There is such a thing as bundle morphism, yes. And that means something, yes. So first we define the action of G on the Cartesian product of the principal bundle and a vector space by the following. Look at that. That's a little bit different. So G acts on the right of U, but G inverse acts on the left of X. Like that. X is a vector. So, yeah. So the inverse on G comes from the assumption that we have left action on the vector space, which is kind of typical, like matrix multiplication on vectors. We don't usually multiply matrices on the right of vectors, right? You take a matrix, you multiply it on the left, pretty much. Anyway, to see that this up here defines a right action, this calculation is enjoyable. We should at least understand this much. So you get G1, G2 there, right?